on to the next session of the applications in the course. So we will talk about fluorescence spectroscopy, which is one of the important application of the field of medical optics. Today I will be talking about one of the inelastic scattering. So if you remember, in the earlier classes we talked about two types of scattering. One is elastic scattering and another is inelastic scattering. In the case of elastic scattering, we have something known as Rayleigh scattering and Mie scattering, and then in the case of inelastic scattering, we have Raman scattering as well as fluorescence spectroscopy. So today we'll talk about fluorescence. So when you see the fluorescence spectroscopy, you have this cuvette, sample cuvette, and the cuvette, we actually pour the sample within this cuvette. So that is one of the important aspect of fluorescence spectroscopy. So everything is based on the sample material. So whether we apply some kind of dye in the sample which actually binds to this analyte for making a biosensor that we will see in some time back, or there is some kind of an endogenous fluorescent dye already present within this sample itself. Okay, so the fluorescence spectroscopy involves the basic components like light source. Okay, you have this light source, and then you excite this to a cuvette, as you see over here, and based on what the sample is including, whether it's endogenous or exogenous fluorescence dye. Endogenous means it is itself autofluorescence, so it's kind of the sample itself will autofluoresce. Exogenous means that we are adding something external from the outside so that it binds with a particular analyte and then it will fluoresce, right? And what we will have in the filter is that and the output of this cuvette would be the light scattered from this light source. For example, if it is a green light, so the green light will be scattered in all the direction. In addition to the green light, there would be higher wavelengths of lights, for example in the red color, and that we actually allow to pass through and get detected. Okay, so on the right hand side we have a Jablonski diagram of a fluorescence spectroscopy. So the electrons on the ground state goes to the higher energy excited state, and then it goes to this ground state of the excited state, and then either it comes down after some time, so that is kind of a very quick transition, and this actually gives the fluorescence, or it goes to a triplet state which to give a phosphorescence. Phosphorescence is like for a longer period of time, but fluorescence is kind of a very short period of time. So this is how the principle of its working. So what you have, the first thing that you have is a broadband light source. So either you can have a broadband light source, or now people are going for making a narrowband light source as well. So for example LEDs, so they start to move to LEDs for making a fluorescence light source. So you for example you're using a broadband light source like a halogen lamp, then you use this collimating lens and an excitation filter. Now even if you are using LED light source, you are still going to use the excitation filter because you want the light source from a very narrow band to pass through and interact with your sample, right? So you have an excitation filter over here, and then you focus your light using a focusing lens to a sample. So this blue region over here is the sample, and then the light is going to scatter in all the direction. So we try to capture it especially in a 90-degree angle, and then using a focusing lens and the emission filter, right? So this is the light emitted by the sample, so that's why it is known as a emission filter. So we use an emission filter, and the light which is focused is given to the detector to detect. Okay, this is the working principle of the fluorescence spectroscopy, right? So there are two main components, that is excitation wavelength and the emission wavelength. Now these two things we will see that it's going to come again and again, and it actually depends on a particular dye, right? So for example, for a particular wavelength we have a particular absorption. So you can see this is an absorption spectra where it has higher affinity to absorb, so within this range of wavelengths, and once absorbed it will actually emit after some time, and this is the range of wavelength that it can actually emit. So there is not kind of a discrete phenomena, but it's kind of a the light will be emitted in a little bit broader spectrum. So, we can actually need to use some kind of filters to allow the light to pass through for a particular range of wavelengths. Okay. So, here you can see this is the excited wavelength, there is a peak excited wavelength that is in the center, and then this peak emission wavelength that is in the center of this particular Gaussian peak. Okay. So, let us see the different kinds of fluorescence molecules that are available. These are the endogenous, that is which is present inside our body, for example, right. For example, you have amino acid, you have structural proteins like collagen, elastin, enzymes, FADH, NADH, lipids. So, all of them are actually fluorescence molecules. So, if you excite it at 280 nanometers, you will get, for example, you excite the tryptophan at 280 nanometers, you will actually get the light of light at 350 nanometers, right. So, flavins, FADH, NADH, so all of them are kind of used especially to diagnose oral cancer, cervical cancer on the surface, because it actually based on fluorescence. So, there is an imbalance in the production of these molecules in the case of normal as compared to the cancerous region, right. So, using fluorescence we can actually try to image the tissue, which area is normal, which area is cancer, based on the absorption of this fluorescence light, right. So, these are the endogenous fluorescence molecules available, and then there are exogenous fluorescence molecules. The good part of the exogenous fluorescence molecules is that it has a wide range of excitation and emission wavelengths. So, we can actually choose whatever we want based upon the filters that are available. As you will see in some time that not all the wavelengths of emission filters, that is band pass filter, long pass filter, and excitation filters, and notch filter, band pass filter. It's not for all the wavelengths is available. So, we have to be kind of very selective based on our application, right. And but the negative part of exogenous fluorescence molecule is that because this is an exogenous, so it's kind of a molecule that is not it should not be given in a significant amount within our body intravenously, right. So let us see a few of the application of exogenous fluorescent molecules. Now, this is a fluorescein molecule. It has the peak absorption at around 470, 480, or actually 490 actually, and it has a emission peak at around 520, so kind of very close by the peaks, right. And this has been used for detection so this is for actually angiography for the eye. So, what do they do is that they use intravenously, they apply this dye around your this dye around your eye intravenously, and then image this using a particular modality, right. So, and you can see this bright colors that is illuminating the blood vessel, right. So, that is only because of the dye that we have been using. So, there is a significant increase in the contrast to differentiate the blood vessel. So, you can actually do the angiography, which also means you can understand where is the blockage within the eye. Okay. One more molecule is kind of very significantly used molecule, that is indocyanine green over here. So, this is the molecule where which has excitation around 780 nanometers. So, it also depends on the how much is the molar concentration of that. So, here you can see that this one is around, if it is 5 micromolar, then it has excitation, that is absorption at around 780. With higher concentration, it has actually around 700 micromolar, and the emission, the peak is around 725 nanometers. So, this is an example of a choroidal blood flow using the ICG within the eye. Okay. So, what you see on the left hand side, left top side, is the molecule chemical composition of the molecule. Okay. One more molecule that has been used significantly is green fluorescence protein. So, GFP protein that you see over here, and this is the yellow color part over here, and this also has been used. For example, it has been introduced within this live molecule. So, this is specifically for live cell imaging. within this landslet, and then you can actually visualize the body which is fluorescing at green color. Right. So this is one more example of using in the live cases. In this case, the fluorescence molecule is given intravenously to the mice, and here you can see that under the UV light you can observe some region to be green in color, right. So that green color is itself because of the fluorescence. Okay. So GFP has the peak absorption at around 400 nanometers and emission at around 510 nanometers. So as you have seen that based upon the dye that we are using, we have to choose, you have to build our instrumentation surrounding that particular dye, and that dye has to have a very good specificity or binding specificity with the molecule that we are trying to image. Okay, so these are something kind of new, that is the quantum dots which have been specifically used. It has dimensions of like less than 10 nanometers. It is more tunable. What do you mean by tunable is that we can actually tune what is the excitation and emission wavelengths. We can actually build a cheaper optical microscope, cheaper fluorescence spectroscopy tool. But the problem with this is that a significant amount of quantum dots can lead to higher toxicity. Right? So over here is one of the example of a quantum dot. What you see, there is a very broad absorption peak over here, and however it actually excites at a very particular wavelength over here, that is around 575 nanometers. Okay, so let us see what are the steps of designing a fluorescence spectroscopy tool. So the first thing is the broadband light source, or as I said, an LED light source. Any one of that you can actually use. Then is the collimating lens. So you need to know what is the focal length of the collimating lens, and then choose it and keep it that particular distance away from your light source. And then you have the excitation filter in the center. So now excitation filter, what transmission characteristics should be using for this excitation filter. So let us try to understand that. Before that, you need to understand what is the dye used in the sample. For example, we are looking for so we are looking for a particular dye like profluorine. Okay, so it has a particular excitation wavelength as well as emission wavelength. Yeah, looks good. So the first thing is to find the sample or the dye which is actually having very higher target binding specificity with the analyte of the sample. Okay, for example, we are using, this is the example of a fluorescein isothiocyanate, right? So it's also known as FITC. It has a peak at absorption peak at around 490 nanometers and excitation at 520 nanometers. Okay, so this is the absorption spectra and this is the emission spectra, right? So you need to choose the correct excitation filter and emission filter. Now the first thing is the excitation filter. So you need to choose the excitation filter which actually couples or it overlaps with the peak of the absorption spectra, right? For example, you can use the one that you see in the blue color, right? This is a transmission characteristic, that is the higher the height of this transmission, that is higher transmission, like 100% transmissions approximately, right? So so this is the case for the excitation filter, right? The next thing is the emission filter. So in the case of emission filter, you can see over here the red color one is that of the emission filter. So this is that again a kind of a band pass filter, but people also kind of now use a long pass filter that you see by the dashed line over here. So the dashed line is long pass filter. So there's people now also, because long pass filter is kind of more cheaper as compared to the band pass filter, right? So next is what are the types of excitation filters available. So here you can see there are 4 different types of band pass filter that I have mentioned over here. So so you can choose accordingly to whatever is the absorption spectra of your dye, right. Similar to this, you have a long pass filter. This is available by Optics India, for example. So this again long pass filter, and you can see this is the characteristic of your long pass filter. So it goes from 0 and then it kind of increases to a very high value around 90%. So it's again you can see that it's not kind of 100%, but only 90% it allows to. And you try to make it as steep curve as you as possible, because if the curve is kind of very kind of a very high slope, if there is significant slope of this curve, then it's very difficult, because your absorption peak is kind of very close by. So you can see this the absorption peak is kind of very close by. So some part of this actual light source from the fluorescence could actually come sorry, the actual light from this Rayleigh scattering could actually overlap with the fluorescence molecule, right. So you need to try to get as much steep as possible, right. So this is the basic part of the discussion of the fluorescence spectroscopy. In the next session, we will talk about how do you actually set up a fluorescence imaging tool for oral cancer imaging. So it would be because it's oral cancer imaging, so we cannot actually have a transmission base. So what we see some time back over here, it's kind of a cuvette example. So we put the sample, analyte, fluorescence dye within a cuvette, and then we try to shine the light on this. But in the case of oral cancer, we actually apply the dye using a cotton cotton pad, and we keep it inside the mouth. We can kind of either sprinkle the dye, or we can actually patch it towards our inner cavities of the oral, and then we have a kind of system which we can actually use it as a fluorescence imaging probe or something like that. So in the next session we will talk about how do we design such kind of a probe, a reflection based probe for oral cancer diagnosis. Okay, thank you.